Hello, today we are exploring topic 3.9, inverse trigonometric functions. As with all functions that we've studied in Algebra 2 and this year, an inverse trig function is the result of switching the input and the output values of the function. As a result, the output values of the inverse function will be the angle measures. So the output values of the trig function will be the angle measures. So let's kind of start here with our sine function. So if we think about our sine function, remember we learned that we had a top value at 1, a bottom value at -1, and we used our quadrantal angles to graph, and we said sine at the circle 0 was 0, and then at pi over 2, it was up here at 1, and then at pi, it was back down here at the 0 line again, and then at 3 pi over 2, it was down here at -1, and then when we got back to 2 pi, we had completed one circle. So we had a sine graph that looked something like that. So if we think about the points, or almost parent function points, if you will, so we can say theta and then sine theta, or x and sine x. So our x values here, remember, are our angles, and our output values are these values up here. So at 0, we're at 0. At pi over 2, we're up at 1. At pi, we're at 0. At 3 pi over 2, we're at -1. And then at 2 pi, we're back at 0. So these are what we would probably consider our parent function points on this particular graph. So if we apply this fact that we know that we can switch the input and output, so the inputs are our angle, the outputs are our sine value, then if I do that, then that means all of my angles are now the outputs. So I'm going to have 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then our input values are going to be 0, 1, 0, -1, and 0. So if we decide, let's go ahead and graph that. We know what it looks like this, but now let's graph it over here so we can kind of see what's going on. And so we know our input values are going to be 1, 0, or -1. And our output values are going to be, the vertical angles. So that means at 0, we're at 0. And this would be at 1, we're at pi over 2. Remember, this would be pi. This would be 3 pi over 2. And this, let's see, I think I have 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay? So at 0, we're at 0. At 1, we're at pi over 2. At 0 again, we're at pi. At -1, we're at 3 pi over 2. And then at 0, we're back up here at 2 pi. So if we look at this graph, here's our S-shaped graph. Here's my 2 pi. It goes like that. So you can see that when we change the domain and range, this is our resulting factor. And so I'm hoping as you look at this graph, you'll be able to see that there are problems when we invert with this periodic graph. Mind you, this is just one period. But what's going to happen? It's going to happen again and again, and we have this stack of these waves going on, and that we can clearly see that this output value of 0, this input value of 0 has multiple output values at the same point. In Algebra 2, you talked about that being failing the vertical line test, but basically our definition, remember, for a function that every input has only one output. And so right now we can see that this input has multiple outputs. So that becomes problematic. And so we have to address not only the nature of these functions, but the fact that they're periodic functions and then they keep repeating. So in order to be able to still use the concept of graphing, functions that are inverses, we're going to have to do a little bit of work in restricting and looking at a principal piece of the graph. So first off, let's talk about two different notations for inverse trig functions. You can see negative sine -1 of x, or you could see arc sine of x. Those mean the same thing. And this notation is read arc sine of x. So that's what happens when you read that notation out loud. So notice that right here we have sine -1 of x. That -1 is again between the sine and the x. It's not on the outside. For instance, sine of x to the -1 is 1 over sine x. So that's what this means. And we want to be really, really careful that we don't confuse where that -1 is and the meaning of it when we look at where the -1 is located in the problem. So if it's to the back of it, it's the reciprocal. Here, it's the inverse. So this is reciprocal. So we want to be very mindful of that. So we can do cosine to the -1 of x, tan to the -1 of x, arc sine of x, arc cosine of x, or arc tan of x. So these are the two notations. And you've got to be able to work with both of them because they do both get used quite a bit. So for example, in example 1, this statement, sine of pi over 6 equals this. So remember, it's sine of an angle equals a ratio. And so writing this in its equivalent arc sine form could look like sine -1 of 1/2 equals pi over 6. So we could be finding the angle when we use the arc sine right here, or it could be written arc sine of 1/2 equals pi over 6. And so what this is saying is, as we're getting ready to talk about, we're going to have to restrict the domain to deal with this whole situation where we find ourselves with one input having multiple outputs. So we're going to restrict some things here to make that happen. So what this actually means is what angle has a sine value within the restriction of 1/2. So what angle has a ratio of 1/2 within the area that we restrict the graph to? So first off, definitely making sure you understand the two new notations and how they work and what they are, especially like understanding when you read it. And then 2, we need to understand how we're going to restrict the domain. So there are pieces of the graph that are considered, I don't know, principal periods of the graph, principal pieces of the graph, and that's what we restrict each one to. So we're going to go through our notes here, and we're going to look at the 3 main graphs we've studied so far, sine, cosine, and tangent. We're going to learn what the acceptable restriction for each one would be, and then we're going to kind of visualize that graph and what it might look like when it's graphed so that you can get the full picture when you're working with actual functions and when you're working with the restricted function. All right, let's start with the sine graph. So this first one is a sine graph. We have a picture for you to look at so you can visualize what's going on. We are going to create a list of parent function points that will be used for our inverse, because remember, inverse is where we're switching the input and the outputs of a function. So the principal period that we're going to be looking at, it starts at -pi/2 and goes to pi over 2. So if you will, think about taking this, cutting it right here, and cutting it right here. And so that piece that falls in between is what's considered the principal period. So we're looking at this point right here, this point right here in the middle, and this point here. So we're going to use those 3 values. So for sine x, we're going to have x and sine x values. But we're just going to use the points off the principal piece right here. So at -pi/2, the y value is at -1. At 0, the y value is at 0. And at pi/2, the y value is at +1. And so just like we have talked about when we interchange the domain and the range, then the angle values are going to become the output. So this is going to be, and you can use whichever notation you would like. I'll try and use a little bit of each through the lesson so you can get comfortable with either one. And so just so that we can kind of visually see what's going on, that means the sine x values are now my inputs, and the angle or the x values are now my outputs. So I'm going to have a -1, a 0, and a 1, a negative pi over 2, a 0, and a pi over 2. And this is an easy way to do an inverse graph. If you figure out the main points that you need, you can exchange the domain and range, and you can easily see what points that we need to plot. All right, so as we look at those points and we plot them at -1, I need to mark this down here very well, did I? So let's move this down just a little bit so while you're looking at me graph, I can get my point past those numbers. And so this is going to be negative pi over 2. All right, so -1 is going to be down here at negative pi over 2. So it's going to be right here. At 0, 0, we're going to be here. And then at 1, pi over 2, we're going to be up here. So when we graph that, then think about what those points would look like. So this is going to kind of wiggle and end up right there. So as you can see, now that we look at this inverse graph, sine of -1 of x, we can see that it's going to pass the vertical line test, and we have a little piece or segment that we can graph. So to make the inverse function, we restrict the function to the domain negative pi over 2 to pi over 2 in the figure, which in essence restricts our inverse function. All right, so let's move on to the next one. So the next piece that we're working with is in the cosine graph is going to go from 0 to pi. And they aren't restricted in the same places, so you do have to learn each restriction that goes with each graph. So we're actually looking at this section of the graph that goes from here to here. So this little piece of our graph, which again is going to have the three points that are going to be here, here, and here. Okay, so cosine of theta, excuse me, let's stick with and be consistent with the x since I called this graph x right here. All right. So this time we're looking at cosine and looking how we're going to restrict that. And so we're going to have x cosine x for our table values and these 3 points. So at 0, we're going to be at 1. At pi over 2, we're going to be at 0. And at pi, we're going to be at -1. Okay, so as we've talked about, now we can do cosine -1 of x. So that's one way we can say it. And then our cosine values are going to become our input, and our angles are going to become our output. So I'm going to write that here. So now that we're looking at our angles, they're going to be back here at 0, pi over 2, and pi. And then this is going to be 1, 0, and -1. So keep in mind, just like above, where we could say arc sine of x, we can also use this notation or say arc cosine. That one you do have to watch out for. Sometimes I mess that one up and I don't get enough C's in there because notice it's arc and then cosine. So do pay attention to that. And now we're going to set up our graph. So we're going to come over here and we're going to have values at 1 and at -1 and 0. And then we're going to have values at pi over 2, pi. Okay. And so pi over 2 and pi. So now we're going to plot our points from our new graph or our new table where we inverted the domain and the range, or we exchanged the output and input values. So at 1, we're going to be at 0. At 0, we're going to be at pi over 2. And at -1, we're going to be up here at pi. And when we connect these points, there we go, a little wiggle kind of going through that point like that. So that's what our graph there would look like. And remember again that now the outputs would be my x and my angles would be my y. Okay, so keeping that in mind, same thing is true that when we restrict our cosine value, we're going to restrict the domain from 0 to pi. So from 0 to pi, that's this area right here. And so that's what our restricted cosine graph is going to look like. So they look very similar. Wiggle is a little different. The piece of the function that they use is a little different. These are the standard accepted abbreviations. So you'll be consistent when you use them. And now we're going to look at our third function we've been studying, tangent. Okay, so we've already talked about how the tangent functions are different because it has all of these asymptotes. And so it becomes actually a little easier to restrict this one because we're going to restrict it between vertical asymptotes, and we're going to use our principal piece or our main piece to be the one right here that goes through the origin. So we're looking at that piece right there, which means my restrictions are going to happen between this vertical asymptote and this vertical asymptote. So not only will the points that we use, which are going to be right here in the middle, so at the center, and then halfway to the graph, so halfway to 1, and then halfway down. Okay, so these 3 points are the ones that we're going to be using right here, but we're also going to use our vertical asymptotes as part of our parent function points. So if we're going to do tan of x, then this is going to be our x's and this is going to be our tan x values. But in the table, we're going to start at the asymptote. So we're going to start here at negative pi over 2, and we're going to state that it's undefined. And then we're going to go to what would be halfway between 0 and negative pi over 2, which should be negative pi over 4. So we're going to have in our function here, right, we're going to have negative pi over 4, and it has a y value down here at -1. Then we have our 0, 0 point in the middle, and then halfway between 0 and pi over 2, we positive pi over 4. So then we're going to have pi over 4, 1. And finally, we're back at the next asymptote, which will end the period that we're looking at for our primary piece. Because again, if we keep repeating in different periods, then we're going to run into that same situation as we talked about earlier, where you'll have one input that has multiple outputs. So at pi over 2, then we're back at that vertical asymptote that's undefined. So I'm going to mark those in here on our original table, just so we'll remember why they're undefined. Okay, so now if we want to do the inverse, that could be tan -1 of x. And so that means the angles are going to become our output, and the input values, the output values here will become our input values. So that's going to be tan x and then x. So all of the angles are going to go to the back and be our outputs. So negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. And then our input values, now this is going to be undefined. This one is going to be -1, 0 right here, +1 right here, and undefined again right here. So when we are setting up our graph, we're going to have to allot for those undefined values now in terms of our values that we're looking at in the graph. So it'll be physically part of it. And remember, we can also say that this is arc tan x. So tan to the -1 of x, or arc tan x. So as we have the graph set up, then we know at negative pi over 2, so that's down here. It's undefined, so that's where our vertical asymptote is going to be. It's going to be here at negative pi over 2, and then again up here at pi over 2. And then we're going to have the point negative 1, negative pi over 4, 0, 0, and then at 1, pi over 4. And so, unlike the other ones, this is going to wiggle up, but technically it can go on forever in this direction and this direction, getting closer and closer to those horizontal asymptotes. So this one looks a little different when we're restricting everything and making sure that it's all lining up. So when we restrict the tangent function, we will restrict the domain to go from negative pi over 2 to pi over 2, this one little piece right here. And we have to be mindful of those vertical asymptotes, which are happening at the two places where we're restricting the graph. All right, so that's how it looks physical graph and how we can use the points to get to our graph and the two new notations. So you can see visually how it's restricted, how those parent function points are going to invert the input and outputs to create a restricted graph or an arc graph or a tan inverse graph. Okay, so we do have to make sure we're good with that. So since a lot of the things that we do when we are working with our functions is actually on a unit circle where we'll have our angles that we're looking at, the same restrictions, for instance, this tangent, remember we said it was restricted negative pi over 2 to pi over 2. In the tangent graph down here, it's still restricted, but we have what we call a restriction mark. And it's an arrow that starts at the lower bound, which is negative pi over 2, and it goes this way around to the upper bound. And notice there's an arrow at the top because that's showing the direction of the restriction. So when we're looking at the values here, this is another way to look at the restriction. So anytime you are doing a problem or you are solving or evaluating like we're getting ready to do, you're going to draw a little picture, you're going to draw a line where the angle is, and you're going to have a restriction mark on your paper. And all of that is in the same graph. I do not want to see a set of axes that has a restriction mark and then a set of axes that has an angle. That's not the point of the restriction mark. The point of the restriction mark is to show that the angle you are actually applying or looking at or drawing is within the restriction. Okay, so then if we're going to look at how those marks look on cosine, we start here, we go around to pi, and again, sine would go from negative pi over 2 to pi over 2. So those are the restriction marks that we're going to look at in these next few problems. All right. So as we look at the next set of problems, notice that the directions say to evaluate. So it's always important to know the wording. So we're saying evaluate means we're not solving an equation. We're taking the expression that we're given and evaluating it for that situation. So as I'm working this, I'm thinking, okay, so what angle has a cosine value that's negative root 2 over 2 within the restrictions? So I'm going to start first by looking at where would those two angles be. So cosine could be negative in quadrant 2, or it could be negative in quadrant 3. So what would the pi over 4 angle be in the second quadrant? That would be 3 pi over 4. And what would the pi over 4 angle be in the third quadrant? That would be 5 pi over 4. So now let's look at that restriction mark. We said that cosine is restricted from 0 to pi. So I'm going to start here at 0. I'm going to draw my restriction mark around here to pi. And so which of those two angles could possibly be the solution I'm looking for in this particular situation? Would it be the 5 pi over 4 that's outside the restriction mark, or the 3 pi over 4, which is within the restriction mark? So hopefully you can see that that's going to be 3 pi over 4. Okay, So let's move on to the next one. So now we're looking at an arc sine or arc to the -1 of negative root 3 over 2. So we're saying what angle could have a value that's negative root 3 over 2 within the restricted area. So here's my axis. And I know that negative sine has a ratio of negative root 3 over 2 in the third quadrant and the fourth quadrant. And so what would this angle be? 4 pi over 3, good. And in this quadrant, it would be 5 pi over 3. And so our restriction mark for sine goes from negative pi over 2 around to pi over 2. So it's going this way. And I can see one angle that's definitely within the restriction marking, which is what this arrow is. So we know we can discount this. This can't be part of our solution. This actually falls in the solution area, the restricted area. However, we have a problem. 5 pi over 3 is way larger than pi over 2, which means we can't use that as our value. But if we start here and we go in the negative direction to get to where that angle is, that's going to be negative pi over 3, which actually would fall within our restriction. So we have to be careful. Just because the line happens to fall within the restriction mark, we also have to look at the value of the angle and make sure that falls in the restriction mark as well. And in this case, it didn't. So our actual answer for this one is going to be negative pi over 3. All right, so now let's look at a tangent one. So we're looking at a tangent arctan of -1, or sorry, arctan of root 3, or tangent to the -1 of positive root 3. So as I'm drawing my axis, then I want to know where is tangent positive. We know that tangent can be positive in the first quadrant, and we know that tangent can be negative in the third quadrant because of positive divided by positive. Remember, tangent is the ratio of the radius. So positive divided by positive gives me positive here. Negative divided by negative also gives me a positive here. So what is the value that has a tangent value of root 3? So what I'm saying there is I'm saying, okay, what has an angle that has a ratio of root 3 in each of the restrictions? And so last time we spent time building the tangent function, and we know that this is going to be pi over 3. And then what's the multiple of pi over 3 that's in the third quadrant? 4 pi over 3. Okay, so now we're going to take a look at those two angles within our restriction. So here's our restriction, which is going to go from here to here. And so here is the angle that falls within my restriction mark. And does this fall within the boundaries? Is this particular point between negative pi over 2 and pi over 2? And it is. It's right here in this group. So that means our answer is going to be pi over 3. All right, so now what are my expectations? My expectation is that you have a graph, you have a restriction mark. Now, maybe you can tell right up front and you don't need to draw both angles to figure out which one's within the mark, and that's fine. So you might just have a graph as simple as that, and that's quite all right. If it helps you right now until you get more comfortable with this, putting both angles that might possibly be there on your paper and then narrowing it down with the restriction mark, that's totally fine. You will have a set of axes, you will have a restriction mark, you will have a line with the angle measured, and then our final answer. Okay, that's the expectations right now for my class. All right, so now let's move on to this next one, which is arc sine of -1/2. So that means we're going to have our axis marked here. And we know that sine is negative in which two quadrants. And then we also know that sine has a restriction mark from here to here. So if we know that that's where the restriction is, and I know that sine can be negative in the third and fourth quadrant, which one am I actually worried about? The angle that's in the fourth quadrant, which happens to be 11 pi over 6. Okay, so now that I've designated that that's 11 pi over 6, I hope that you can see, 11 pi over 6 is way bigger than the pi over 2 restriction that we have. So that means I'm going to start from here and I'm going to go down here to my negative pi over 6 angle. And so that would be my answer there. So the only time that you don't have two possibilities to narrow down from might be if you're looking at a quadrantal angle that's actually going to be graphed on the axis itself. All right, so let's see how you're doing. So let's go ahead and I'm going to pause my video and I want you to pause your video as well. And I want you to do problem E and F. So I want to see a picture. So notice how I narrowed down my picture. I don't have both angles. If this makes more sense to you and you feel more comfortable drawing both angles right now, be my guest. But you must have the restriction mark, the graph, the angle you're talking about, and the measure of that angle. All right, pause your video and work on E and F. All right, let's see how you did. So cosine, arc cosine -1. So what angle has a cosine value of -1 within the restriction? And that happens to be here at pi. And then here we do arc sine, and arc sine has a positive √3/2 within the restriction in quadrant 1, which is happening at pi/3. Okay, so now let's look at arc cosine and talk about that. So remember that when we say arc cosine, what this means is we have some cosine value, some angle that has a cosine value equal to 2 within the restriction. So now if you think about our graphs, if you even can go back to this note page right here, what was the maximum value for a basic sine graph? It was 2. What was I'm sorry, a 1. What was a maximum value for a basic cosine graph? 1. What was the minimum graph for a basic cosine graph? -1. What was the minimum for a sine graph? -1. So if I'm asking you what has a cosine value of 2, then we have a problem because this hasn't been any transformation to it. So we know that the tallest the cosine graph ever gets is +1, and the lowest the cosine graph ever gets is -1. So then what do we know about this 2 it's asking us about? It means it's outside the range of the function. So we're going to use the empty set symbol. So there is no value that makes that work because it's outside the range of cosine of theta. Okay, so what does that mean? That means, therefore, no theta will work. Okay, so that's just thinking through the confines of the cosine graph and realizing that that too means you're talking about something that's outside the range. It's beyond the top value of the cosine graph, the original cosine graph. All right, so what do we know about arc of 2 then? Same thing. So this would be the sine of theta that equals 2. And once again, we know that the top value in sine is 2, which value in sine, excuse me, is 1, which makes 2 above that value or outside the range. So the same thing would be true. We would say the empty set, and the reason it's outside the range of cosine of theta, and I'm sorry, of sine theta. We're still looking at the previous problem. Sorry about that. Sine theta. And therefore, we know that there are no thetas that will work. All right, so that gave us a little, another piece to kind of think about as we're going through the graphs here. All right. So go ahead and take a first and second read through on example 3. Pause your video, do your first and second read, and then we'll come back and talk about it. Pause your video. All right. So as we're looking at the points here and the things that were given in the graph here, we're talking about standard position angles. So opening from the positive x-axis around, we're looking at points are at the terminal side of the ray and that angle. And then we're reflecting those points over the y-axis, the origin, and the x-axis respectively. So if this is the point, xy, then if we reflect it over here to this quadrant, that would be the point negative x positive y. And if we reflect into the fourth quadrant, then we know that's going to be negative x, negative y. And if we reflect down over here, then we know this is going to be positive x, and then that's going to be negative y. So those are the coordinate points. We've looked at those in previous problems, so that should be nothing new. So question 1 is saying cosine negative 1, so the inverse of cosine of x. So what does that mean? That means what angle has a cosine value of x? All right, so I went ahead and wrote down what we're talking about. So what angle has a cosine value of x within the restriction? So the restriction here, it goes from 0 to pi for cosine. And so as I'm looking at my graph here, keep in mind that I had been restricted from here to here. So then what would the cosine value, what point would that cosine value be? We can see, because we know where our restriction is from here to here, there are two possible angles or two possible points, point P and point Q. Which one has a positive x value? So that's going to be point P. Okay. So then the next one, I'm not going to write this statement out each time. I wanted you to have it once in your notes so that you would be aware of what we're talking about. But this one is saying sine to the negative 1 of negative y. So this is saying what angle has a sine value of negative y within the restriction. So remember, the restriction for sine is going to happen from here up to here. Okay, so that's within the restriction. So if I'm looking at this graph right here, I'm going from here to here, I could be talking about the point P or the point S. So which one of those has a negative y value? And that would be point S. Okay, so go ahead and pause your video. I want you to redraw the restriction mark under each one and answer the question. So go ahead and pause your video. All right, so how did you do? Did you get your restriction marks labeled correctly? And did you pick point Q for C and point S for D? All right, so notice right here, this is saying that what angle has a tangent value of negative y over x. So you had to look and see which one of those slopes would be positive and which one would be negative in order to be able to answer that question, okay? So hopefully that makes sense. Moving on to example 4, our last set of problems here. And here we're going to evaluate the following. And the following just happen to be, some of them are compositions and some of them are straight angles. So as with any restriction that we do, any composition that we do, we always start with the inside function. So we're going to start with this part. And remember, what that means is what angle has a tangent value that equals square root of 3 within the restriction. So since this is arc and this has a restriction, then I'm going to have a graph that has my restriction mark on it, not a suggestion, an expectation. And so there's my restriction mark for tangent because it goes from negative pi over 2 to pi over 2. And so now I want to know within those two quadrants, where is the angle that has that positive root 3? And so I know it's going to be right here, and that's going to put it at pi over 3. But wait, there's more. That is not the answer. What that means now is that we still have this piece. So I have the tangent of pi over 3. Well, the tangent of pi over 3 does not have a restriction to it. So we have to think about what that might look like. So pause your video and think about what is the angle, or the angle pi over 3 that has a tangent value or a ratio of what? So now we're looking at this part right here. So pause your video and see if you can figure that one out. So hopefully you know your tangent value. So if you go to your first quadrant, tangent 3, or first quadrant angle of pi over 3, it has a tangent value. And so this ends up being square root of 3. All right, let's go to the next one. So we're going to start in here with arc sine of negative 1/2. So remember, that just means what angle has a tangent value of -1/2 within the restriction. So we're going to have a restriction here. And for tangent, remember that we're restricting it from -π/2 to π/2. So within that restriction, where would there be a tangent value that is going to have this angle ratio that we're looking at, or we're looking for, I guess? So we know from our study of the unit circle that in the fourth quadrant, we have an angle which is 11π/6 that has a tangent value of -1/2. However, 11π/6 is bigger than the π/2 angle, so that means we're going to have to go backwards and look at the -π/6 angle. So that means now we have sine, so we're going to have sine of -π/6. And so then we would need to know what that is. So going backwards then, what would that value be for the -π/6? Well, it should be the same thing as the 11π/6. That's how come we can use that little piece of information working in the negative direction. So in this case, it's going to be -1/2. So before you make a jump and say, hey, I notice that these two things are just canceling each other out and you have a value here. Many times that is the case, but not every time. You have to be sure that you're paying attention to if something has a restriction or not. And if it doesn't have a restriction in one place, but it needs one for the other part of the composition, then it might not actually turn out to just be unraveling. So I always suggest definitely working through the process so that you know, because if you have a function that's outside the restriction, then that's going to affect how those cancel each other out. All right, so go ahead and pause your video, and I want you to do C and D, practicing just like we have. So notice, now you don't have to write this statement. I just wanted to make sure you understood what you were looking for, but you would need to have your graph with your restriction marks and your angles, and then the rest of the composition, so sine of whatever that was that you got there before you answer your question. So there are, some steps that do need to be there and not just a piece of scratch paper with a bunch of doodles on it. Okay, make sure you've got your graph that represents the problem. All right, guys, pause your video and do C and D, and we'll check back in here in just a moment. All right, so let's see how you did on C. So the first one was not restricted, so the sine of π/6 is just 1/2. This graph was not necessary. I just was making a point in my notes so you would remember where that was. You could just say sine of π/6 equals 1/2. But then you're looking at arc sine of +1/2, so that is restricted. So this piece would actually need a graph. So our restriction goes from -π/2 to π/2. We're going to find that angle right in here that has a sine value of 1/2. So my answer is π/6. So notice in this particular problem, just because it's arc sine and sine, it did not unwind and end up with being 7π/6. So inside no restriction, so the sine of 7π/6 is -1/2. Remember the restriction is from -π/2 to π/2, so it wouldn't have been, since it's not restricted, I mean, that's not necessary. So I just was showing you or reminding you where that angle was, but this is really all that we need in our work. And then we're going to say arc sine of -1/2. So that's this piece right here. So that is restricted. So I'm going to draw my axis. I'm going to draw my restriction mark. And the angle that has a sine value of -1/2 on the unit circle in one of these two quadrants is 11π/6. But remember, we're restricted on that from -π/2 to π/2. 11π/6 is way bigger than π/2. So that means we have to use the negative angle. So the answer to D was -π/6. All right, so go ahead and I'm going to have you work E and F. So pause your video and answer those two. We'll come back and check in just a moment. Pause your video. All right, let's see how you did. So no restriction for this part. So the sine of π/3 is just √3/2. So arc cosine of √3/2 within the restriction from 0 to pi occurs when the angle is π/3. So that's my answer. Here, cosine 5 pi over 4 has no restrictions, so the cosine of 5 pi over 4 is negative root 2 over 2. So then the restriction for cosine is 0 to pi. So within my restricted area, what also has a cosine value of negative root 2 over 2? And that happens to be over here at 3 pi over 4. So once again, you can see that those are not the same angle. So really follow through with that process and make sure in your composition, you're not losing sight of angles that don't necessarily fall into place. Okay. So last two, we have an arctan. So remember that just means when is the tangent value of theta equal to 0? And then we have another one, arc cosine of this. So remember that just means the cosine of theta equals negative root 3 over 2. So go ahead and pause your video one last time, answer these last two questions. We'll be back in a moment to check in and make sure we're all good to go before we wrap up our lesson. Pause your video. All right, so this one has a restriction from negative pi over 2 to pi over 2, and tangent is 0 at 0. So that's our answer. And why couldn't we use 2 pi? Because 0 and 2 pi have the same tangent value of 0. Well, 2 pi would be definitely bigger than pi over 2, so it must be the 0 that you give as your answer. Okay. And then this last one, so what angle has a cosine value of negative root 3 over 2 within our restriction of 0 to pi? That happens to be this 5 pi over 6. All right, so I've given you lots of examples of how your work should look and what's necessary in your work. Make sure that you're doing that when you practice your daily practice and your check for understanding. And we will start solving trig equations and inequalities in our next lesson. Thanks so much, guys. Bye.